Okay. Thinking back to section 3, when we were talking about approximating the area under the curve with a series of smaller and smaller and smaller, we did rectangles, right rectangles, left rectangles, midpoint rectangles. You could have also done trapezoids. We didn't really talk too much about those, but you could do trapezoids because a trapezoid actually is an even better fit. Because if you do a trapezoid, you don't have the part of it's left out and part of it's left in part. It gives a better approximation. Numerical integration is kind of based off of that, and we can utilize the trapezoid rule that says that you take, the area, the number of trapezoids under the curve, as long as the distance between, as long as the base of the trapezoids is all 1, basically. So, same ideas with the rectangles. If you use 6 trapezoids for 1 over the x dx from 1 to 5, then you would get this approximation. If you did 8, you would get this one. If you did 10, you get this one. If you did 20, you get 100, you get 1,000. By the time you get to 100 or 1,000, you realize the area is going to be 1.609 with very little difference between the two. So if we did the same thing with n equals 4 rectangles, then all we're going to do is we're going to graph this function from 0 to 2. We're going to divide it up into 4 intervals, into 4 short intervals, and going from 0 to 2, that means you're going 0 to 1/2, 1/2 to 1, 1 to 1.5, and 1.5 to 2. So this is how we're going to wind up. There is. That's what we're going to do here. Calculation by hand says that you let the first value be 0, so that your first trapezoid goes from 0 to 1. And wait, I don't think I matched up the endpoints. Let me. Yeah, it says 0 to 2, and then the table goes from 0 to 4. But that's the 4. So the first rectangle, the first increment, is from 0 to 1/2, and then 1/2 to 1. So the base of the trapezoid is always going to be 1/2. Okay? So in order to find out how tall the various endpoints are, you plug in the value of 0, 1/2, 1, 1.5, and 2 into the formula, and you get the height of those lines. So basically what we're saying here is that the length of this edge is 1, because that's where x equals 0. And the length of the edge of a trapezoid here is going to be 1.11803, because that's where x is equal to 1/2. And then this is where x is equal to 1, and it's going to be, the length of the line there is going to be 1.41 and 1.802, and then the last one is going to be 2.23607. And you would just plug those into the trapezoid formula and get the area of the trapezoids. So by doing that, you've got 1/2 times 1 plus 1.11803 plus 1.4121 plus 1.8027 plus 1/2 again times 2.23607. And 2 minus 0 was the interval, and we divided it up into 4 intervals, so the approximation is 2.9765 using the trapezoid rule. It's all just arithmetic and geometry. Okay? That's all that is. But if you can use the calculator, you could just as well do it the way that we did it with rectangles. You just put in the formula and use the fact that the interval is b minus a divided by how many rectangles, and use the command to sum up whatever is in list 3. But on the calculator, there's also numerical integration. Simpson's rule says that you're going to use n equal 4 trapezoids to approximate that area, which is an example, the same one as example 1. Simpson's rule is just a different formula. It gives a better approximation. And the only reason I covered this section is because I wanted for us to do an application problem where it actually had some meaning. What does the area under the curve actually mean in calculus? So we have a sales manager, and he has these results. Total sales over the given period says that you would need to plot those points. Okay, the way that we'll do that on the calculator, not by hand, for those that have not had statistics yet or don't remember, we're going to go to Statistics, choose Edit, and if you've got anything in your first list, clear it out by putting the cursor on List 1 and go down in the list so that it's blank. His years are 1, 2, 3, 4, 5, 6, 7. And his rate of sales, which is a derivative value, at the end of year 1 was 0.4. The end of year 2 is 0.6. The end of year 3 is 0.9. At the end of year 4, it's 1.1. At the end of year 5, it's 1.3. And then 1.4. And then 1.6. And in order to see a graph of that, we're going to go to the window and we're going to let X-min be 0. X-max is going to be 8. We're going to count by ones. Y-min is going to be 0 and Y-max is going to be, let's say 2. And since this is going in tenths, I'm going to let it increment that by 1/10. So if I want to see the graph actually, then I have to press second and Y equals and go to stat plots. And right now all my stat plots are off, so I open the first one and I turn it on. Are you there? Yeah. Okay. The first one that's usually highlighted is the scatter plot. It's the very first one after type. So if that's not the one that you have highlighted, put your cursor on it and press enter. Then down arrow and tell it that your X values, which are your years, are in list 1, and your Y values, which are your rate of sales, are in list 2, and let it use the little boxes to mark those different points rather than a dot because it's easier to see those. So then we just hit graph, and we have something in the Y equals menu, so let me go get rid of that. Okay? Now they want us to connect these points with line segments, not a curve. They want us to connect it with line segments. So if you want to see the line segments, go back to stat plot, back to plot 1, and choose the one after the scatter plot, which is looks like a line graph. And then just go on back and graph again, and we see that. The only thing we don't see is we don't see the vertical distance. Okay? The first trapezoid would be from this point to here, and up to there. The second trapezoid would be from here to here to here, and up to there. So just envision some vertical lines, and you'll have the trapezoids. Use the trapezoid rule to find the area bounded by the broken line of part A, the x-axis, the line x equals 1, and the line x equals 7. So we want the total area. I think you can actually draw those lines, but I don't think we're going to really want to do that. We want the total area between this line graph and the x-axis, going from 1 to 7. Okay? So the way that we do that if I can sketch what's on the calculator, and then I'll switch you over to it. Okay, so that's roughly what it is we're finding the area of. And remember that each one of these increments right here, these are all 1. So the base of every one of those is 1. What's different is these other two sides. So the length of this side is 0.4, the length of this side is 0.6, the length of this side is 0.9, the length of this one is 1.1, 1.3, 1.4, and 1.6. And Simpson's rule says that we would use the formula for trapezoids because Simpson's rule is just a refinement of the trapezoid rule. That's really all it is. So B minus A, well, A is 1, B is 7, times the function at these various values, and that's over 3n, so 7 minus 1 over 3. N is the number of trapezoids, 1, 2, 3, 4, 5, 6. Yes, we're doing Simpson's rule. It says to take 0.4, which is the value at f of 0, f of x sub 0, and then 4 times the value of f of x sub 1, which would be 0.6, plus 2 times the value of f of x sub 2, which is 3, and that's 0.9, plus 4 times the value of f of x sub 3. So this is 0, 1, 2, 3, so that's 1.1. Plus, now at the end we're going to have to be back down to f of x sub n, which is going to be 1.6. just the value. So before that, we're going to have 4 times this value, 1.4, plus 2 times 1.3. So it goes 1, 4, 2, 4, 2, 4, 1. So 7 minus 1 is 6, over 3 times 6 is 18, times 0.4 plus 0.24 plus 0.18 plus 4.4 plus 2.6 plus 6.4. No, what was 60? 5.6 plus 1.6. And at that point, we're going to need the calculator. So it's not really a difficult process, it's just kind of tedious. Yes? Mm-hmm. Yeah. No, you'll have all the formulas. Yeah, you'll have Simpson's rule, you'll have all the integral formulas, you'll have the trapezoid rule, you'll have all the formulas. You don't have to memorize any of them. You're going to have a Chapter 15 test by itself with nothing else. A week. And actually, I'm considering that we probably want to do that a week from today instead of waiting until the last day of class. That way, the last day of class, we can review for the final. And I'm sorry, folks, I made a mistake here. It's not 0.24, it's 2.4. Yeah, and it's 1.8. I didn't put my decimals in the right places. My arithmetic brain hasn't been working today at all. So there's the sum, and we're going to multiply that. 6 over 18 is 1 over 3, but we can multiply by 6 over 18 just as easily. And it says the total area is 14.067. So what that means in context of the problem is that the sales over that period, the total sales over the period is about 14.067, and they really didn't give us enough information, so we don't know if that's dollars, thousands of dollars, or what it is. But we'll assume it's certainly not going to be $14.07. At least we hope not. Okay? Ah, I see. Yeah, it's right where the line broke, so I didn't see it. Let me try that again. Thank you. So 6.27 instead of being 14.07. So that's by Simpson's rule. Now, if you use the trapezoid rule The trapezoid rule says basically that you just find the area of each one of those trapezoids, and the formula for the area of a trapezoid is 1/2 times the average of the two differing sides times the base, and the base on every one of these is 1. So the trapezoid rule would be, let's just add up get the side averages first. So it's going to be 1/2 or 0.5 times f of x sub 0, which is 0.4, plus 0.6 plus 0.9 plus 1.1 plus 1.3, 1.4, and 1.6, which is multiplied by 1/2. And then you multiply that times b minus a, which again is 7 minus 1, which is 6, over how many trapezoids we've got. And in this case, we have 1, 2, 3, 4, 5, 6. So that's going to be 36. I'm sorry, no, it's not. It's going to be 6 over 6. Yeah, which is just 1. So it says it's 6.2. So you see the difference between the two approximations is that Simpson's rule is just a little bit more accurate. But it's essentially the same thing. Yeah, if you've got the actual function, it's a lot more accurate. Now, there's a way to automate it on the calculator, but unless there's a really good reason for doing it in the homework, I won't show you that way. You could use the list on the calculator and actually... Mm-hmm. Actually, I think the calculator might even have a Simpson's rule routine built into it. I'll have to look. I'm pretty sure the 84 does. I don't know about the 83. But anyway, that's all there is in that section. So if you want, what we will do is go to my labs and look at some homework problems. Now let's look at 15.3 first, or 15.6, since that's what we just covered. Now, the good thing about this is they actually have these little apps in here that will help you with these. So select the Show Trapezoids option and the Show Area Values option, and use the trapezoid rule with n equals 4 to approximate this equation. So you launch the app, and And Wolfram's not loaded on here, daggone it. I thought it was. Well, you should be able to launch the app. If you were at home, you could launch the app. And what you would do is do exactly what this says. You just slide it to what you want it to cover. You can put in the formula and tell it that you want from, you want 4 rectangles, you want 4 trapezoids, you want 8 trapezoids, you want 10, however many you want. We are sure not going to do that problem if we can't use the interactive figure. And I don't know if I can install it or not. Let me check. Yeah, you can do it with 4, but who wants to do it with 10 and 20? Helps if you spell it right. This is one of those days I can't type either. And if it won't let me install it, we'll just look at some of the others, and I'll get them to install Wolfram on this one. Yeah, it's going to take a little while. We'll look at some other problems. Well, maybe it's going to go ahead. Okay, let's go look at 5. Okay, use n equals 4 to approximate the value of the integral by Simpson's rule, the trapezoid rule, and then the exact value by integration. So with Simpson's rule and the trapezoid rule, we need 4 increments. We're going to graph the interval. Be sure and turn that plot off when you do this. Okay, so there's what the graph looks like, but we're really only interested in going from 0 to 2, so there's no point in looking down at negative 10. So we'll just maybe start at negative 1 and go to 3. And we don't care about what's below the x-axis either, so change that to 0, and we probably only need to go up to, well, yeah, we'll leave that there and see what happens. Hit the graph. Okay, now we can't see the value at 2, so f of x when x is equal to 2 is going to be 9 times 2 squared is 9 times 4, which is 36, plus 3 is 39. So let's raise the window on up to about 40. So the area we're looking at, trying to use Simpson's rule on, goes from here to here. And to make it easier to imagine the increments, since 0 to 2, if we're going to divide it up into 4, we're going to have to go by 1/2. Ah, yeah, it was. Didn't go far enough down. There. So here's what we want to know. And I'll do a little recording here to the side on paper. Okay. I'm going to go to the table, and we want to start at 0, 0.5, 1, 1.5, and 2. So we've got the values that we need now. And Simpson's rule says well, let's do trapezoid rule first. Trapezoid rule says that you're going for the integral from 0 to 2 of that function. You know what the function is. We take b minus a, which is 2 minus 0 over how many intervals? We want 4, times 1/2 times the first interval. So 1/2 times f of 0. Plus f of 1, or I'm sorry, f of 1/2, plus f of 1.5, plus f of 2, but f of 2 has to be multiplied by 1/2. The first and the last are multiplied by 1/2. So then, using the values out of the calculator, the integral from 0 to 2 of 9x squared plus 3 dx is equal to 2 minus 0 is 2 over 4 is 1/2 times 1/2 times 3 plus 5.25 plus 12 plus 23.25 plus 1/2 times 39. So it's 1.5 plus 5.25 plus 12 plus 23.25 plus 19.5. Actually, you wanted to know how to automate it. Go to Stat, and edit. Clear out those two lists we used before. This will automate it to some extent. It won't make it totally automatic, but it will certainly make the math a lot faster. In list 1, you want to put your endpoints of each one of the increments. So you're going to go 0, 0.5, 1. Whoa, whoa, whoa. Come back here. Start at 0. Each one of the rectangles is 1/2 wide. You've got 4 rectangles over an interval that's 2 units long. So that's 1/2. So 0.5, 1.5, and 2. I think I left out 1. 0.5 and 1. 1.5 and 2. Okay? Then put your cursor on top of list 2. At the very top of list 2. And then go to vars, yvars, function, y1, and for the x values, plug in list 1. So put parentheses, list 1. And what this is going to do is it's going to go get the equation that I put in y1. It's going to plug in those x values, and it's going to give me the results in list 2. Okay? And the only thing I have to do now, if I want to do the trapezoid rule, is I have to remember that the first one and the last one are multiplied by half. So I'm going to say that is 3 times 0.5. And then I'm going to go down to the 39. And I'm going to say that that's 39 times 0.5. And then I'm going to ask it on the home page, find me the sum. That's going to be second stat, math, and over to sum, find me the sum of list 2. And then multiply that sum by 1/2. So that's a little bit faster than doing it all the way out by hand and feeding in the numbers. Okay? And you could do Simpson's rule the same way. So to do Simpson's rule, we need to remember what Simpson's rule is. Let's get another piece of paper. Simpson's rule says the integral from a to b of the function is equal to b minus a divided by 3 times whatever number of increments that you've got, and ours is going to be 4, times f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3. And then it just follows the pattern of alternating 4 and 2 and 4 and 2 and 4 and 2 until on the very last one you're back down to f of x sub n, whatever the last one is. So in our problem, we're going to have the integral from 0 to 2 of 9x squared plus 3 dx is equal to 2 minus 0 over 3 times 4 is going to be 12. I shouldn't write and talk at the time. It's going to be 2 over 12 times that sequence. And ours is going to be, since we've only got 5 endpoints, so that's where our terms are going to be. And we can go back to the calculator and we can do it the same way we just did it. We'll go back to stat, enter, go up to the top of list 2 and change them all back to the y values. So vars, y vars, function y1 of list 1. So the first one's going to be left as it is. The second one's going to be multiplied times 4. Third one's going to be multiplied times 2. The next one's going to be multiplied times 4. And we're going to leave the last one alone. So then we're going to go back to the home screen and ask it to find the sum of list 2 and multiply that sum times 2 over 12. And it says the approximation is 30.333. But if you want to know the numerical integral for it, I think we'll just do this on the home screen. We'll just go back to math, find your numerical integral. The expression is in y1. With respect to x from A to B. And it says it's 30. So if you compare the answers that we got, you'll see that Simpson's rule does a lot better job of approximating than the trapezoid rule does, but numerical integration actually takes Simpson's rule and it makes infinite increments, infinite parts. So actually numerical integration,
By the way,
numerical integration actually is based on Simpson's rule. Within approaching infinity. Okay, so it goes to get you right. That would be what? 9x squared plus 3. Okay. calculator's list as a kind of like a spreadsheet. And I hope somebody wrote down what the answers were because I didn't. And all we're going to do different in the one that I've got here on problem number 6 is just swap out the functions. It's going to be a different function. And this time we're going from 1 to 3, and we want 4 rectangles. Let's see. I think I'm incrementing correctly. No, it's 0.5. Okay, and since we're going to, since we're going to use both rules, I'm going to go ahead and copy the values over into list 3 from list 2. That way we don't have to do it again. So for the trapezoid rule, the first one is left alone. I'm sorry, the first one's multiplied by half. And the last one's multiplied by half. And then we want the sum of list 2 and that's going to be multiplied times b minus a, which is 3 minus 1, divided by the 4 increments, which is just going to be 1, so the answer is going to be 8.554. And to do the Simpson's rule on the others, then we remember that the first one is going to be left alone. The second one's going to be multiplied times 4. Second one's going to be multiplied by 2. Third one's going to be multiplied by 4. Next one's going to be multiplied by 2. And you leave the last one alone. You can also, if you don't want to remember having to go to the list, you can also just go to second 0 to the catalog and scroll down till you see sum. And then Simpson's rule says to multiply that by b minus a, which is 2, divided by 3 times the number of increments, which would be 12. And it says it's 2.86. So that's a way more refined version. Or then you can just simply do math. Do the integral of y1 with respect to x from 1 to 3 and get 2.589. So once you understand the process, the arithmetic doesn't have to bog you down. And I think they're only asking you to do 4 increments of 4, so you could keep doing that same thing over and over again on all of these. Let me see if it ever decided to let me have my download. Okay, does anybody have any questions? Okay, here's the game plan then. Thursday, we will review for this test. Let you work in class, working on homework, working on the quiz. I'll work through the quiz with you one time. Okay? Tuesday, test in class. Next Thursday, review for the final. And I will give you a practice final, but you can do, you want a practice final on paper, or do you want a practice final on my lab?
Just final available paper or?
It's up to you.
Yeah.
Okay.
Yeah, will we be able to go on there and review it a few times?
Yeah. What I'll do is I'll just build a practice test. What I'm going to do is I'm going to take the quiz for chapter, I may take 1 or 2 out of the quiz for chapter 11, but probably not much. And then the quiz for chapter 12, the quiz for chapter 13, quiz for chapter 14, quiz for chapter 15, and I will pick some out of each one of those and put together a review. Okay? Everybody show up next time. We're doing the evaluations next time, and I need to have as many people here as I can get here. I need feedback.
With the analysis calculus one, you have to spend the entire semester learning derivatives and intervals, and you literally can do them in like 70 seconds on your calculator.
Yeah.
I need to make an appointment with you. I have to file an appeal for my Hope Scholarship
Okay.
when I transfer to ACU.
Okay.
And I need your signatures.
Okay.
I've got everything.
Okay.
Now, right up. It's not due until the 1st of May, so we've got.
Thursday after class?
Sounds good.
Does that work?
Yeah.
Okay. Have a good evening, Carp.
Look, what the hours? Have a good day.
You too.
I had this turned in a long time. It's 12.
Oh, okay.
It's like the quiz that we did in class and the homework and the notes.
Okay, I'll go add that to what I've got in your grade book then. You're welcome. Hey.
This Unit 3 exam, those
Yeah. Actually, since it's actually past due until you're actually ready to take it, what I do is I just wait until you come and you sit down and take it, and then I open it up then.
Okay, so it's not, I know.
You're talking about the test, the third test, right?
The Unit 3 exam. It
Yeah.
says that I have 3 times to take it.
No, it's not supposed to, although it might. Let me look.
It probably doesn't. I probably misread it.
No, it's entirely possible you didn't, because I had it set up on somebody's for like infinite tries, and that was not good. Let me go look. Because sometimes it defaults to something and I forget to change things. Yeah, it's not supposed. Oh, I know why it says 3, because we got stuck at the end of that test and some people couldn't get back in. That's supposed to be 1. But what I'll do for you is I'll go in that day and just do settings just for you.
Okay.
And then I'll set it up for whatever time it is on whatever day it is. And then,
Okay.
you know,
And
give you the password for it.
Okay. Do I need to do that in class, or can I do it another day? Like maybe a day.
You just need to meet with me, and as long as we can meet somewhere with this computer lab, there's no problem.
Okay.
Okay.
And, well, I'll email you on that.
Okay.
I should be good. Was there any class quizzes or homework that I needed to do?
Not in class, no, because I haven't been doing very many in-class quizzes. We've mostly just been working in class on my math lab.
Okay. Sounds good.
Hmm? Sure. Oh. Okay. Be glad to. Go ahead.
Good thing.
You too.